Hi, everyone. Welcome to the 67th Online Spintronics Seminar. It's a great pleasure to introduce today's speaker. Dr. Lucas Caretta is a President's Postdoctoral Fellow and a Ford Foundation Postdoc Fellow at the University of California, Berkeley, working with Professor Ramamurthy Ramesh. Dr. Caretta completed his PhD in Materials Science and Engineering in 2019 at MIT as an NSF Graduate Student Fellow under the supervision of Professor Jeffrey Beach. There, he made significant contributions to the understanding of domain wall dynamics in compensated systems. Dr. Caretta's current research focuses on manipulating and engineering spin and charge at the atomic scale through the development of advanced synthesis and in operando calculation techniques. So without further ado, Dr. Caretta, please go ahead with the talk.
Thanks so much for the nice introduction. As was stated, I'm a postdoc fellow at UC Berkeley in Ramesh's lab. There I work on a number of different correlated systems, including spin systems. The majority of the data I'll show you today was actually taken during my time at MIT under Jeffrey Beach, where we're really focused on looking at dynamics of solitons in thin films. Now, this work has been done over the course of a few years with the collaboration of many people, including lots of international collaborations, including theorists in Korea. I don't think I explicitly show any microscopy in this presentation, but a lot of microscopy and atomically resolved imaging was taken at Cornell and in David Muller's group. And some of the synchrotron work that you'll see here today was taken in Spain with our collaborators there. So what I'll talk to you today about it is really manipulating spin textures in these materials and engineering materials physics, another phenomenon to really achieve high performance and really access to physics. So most of my research actually focuses on different kinds of ferroic materials, not just magnetic materials. So these can be things like, as we know, magnetic systems where we have spin ordering, as well as other types of ferroic systems like ferroelectrics, which have charge ordering. Now, often when we think of these systems, we think of them as single domain systems, or for example, in magnetic systems, we think of macro spin models and things like that. In ferroelectric systems, we often think about single dipole models. In fact, these types of systems are very rare. Really, they're actually kind of difficult to engineer. For example, like refrigerator magnets, bar magnets are not a trivial thing to engineer. In reality, what happens in these materials is you get what we call complex spin textures or non-collinear spin alignment. So if you really look at the atomic scale, you see that these spins take on twists and windings of all different sorts. And so this can occur in one dimension, such as domain walls, which can be chiral in some cases. In ferroelectric materials, they can even be icing or non-icing, right? So the magnitude of these arrows can change during these transition regions. They can be two-dimensional in form, so you can have textures that look like bubbles or that are even topological, like skyrmions, or have chirality or vortices. And they can even occur in 3 dimensions, where you can observe things like topological Hopfions. And there's many other types of textures, both polar textures, spin textures, such as things like cycloids and spin spirals and things like that as well. And so what really excites me about these materials is not that these textures exist, but actually they're dynamic and they can move. So we can manipulate them, we can stimulate them, we can excite them in different ways, which can help uncover new physics. So really the majority of my research over the past few years has been looking at these excitations, particularly in oxides, to access or serve as a platform really to access new physics. So we can really study things like topology. I'll show you a variety of interface-driven phenomenon today. We can study the interactions between different sublattices of materials, and even what I'll focus on today is really looking at ultra-fast dynamics. And the hope is that by studying these sorts of excitations, we can either have some direct or indirect technological impact, such as scalable devices for memory and logic and other types of impact as well. But really what I think is important is what enables all of this to happen is a combination of 2 things. It's atomically precise synthesis, so creating and understanding materials physics to create the most perfect and relevant materials we can possible. and combining that with a variety of in situ and in operando imaging and electronic techniques. So it's really the power of both of these that allows us to uncover this new physics by accessing these Ferroelectric excitations. And so just as a quick pitch, we can do this in different material systems, not only in magnetic systems, but ferroelectric systems as well. And so, for example, in ferroelectric material systems, we can create what we call ferroelectric superlattices or multi-layers of materials where we can use boundary conditions and strain and other types of effects to essentially create coexistence of different types of ferroelectric textures. So what you're looking at here is essentially a high resolution TEM image of different ferroelectric textures which have different symmetries in this material. This is a cross-sectional view. We can also use in operando and in situ mesoscopic imaging techniques to actually probe these different phases, the different symmetries of these phases, using things like second harmonic generation. And we can even manipulate back and forth between these different phases using external stimuli, thereby changing materials' properties and symmetries by order of magnitude. But really, today's talk is really focused on spins. So we can use a similar platform or a similar understanding to look at spin textures as well. So we can use these very similar in operando in situ imaging techniques, such as Kerr microscopy, as well as synchrotron imaging techniques, if we need to use them, to really uncover physics of the system. And what I'll talk about today is really how we can harness both the synthesis and these imaging techniques to drive domain walls to fundamental limits. In fact, what I hope to prove to you today is we can drive domain walls and other solitons to relativistic limits, really helping us to uncover interesting materials physics and hopefully having some engineering impact. Okay, so here's an outline for today's talk. I'll begin with actually a motivation, technological motivation for why we're interested in studying these particular spin textures. I'll provide some background information on where the dynamics of these systems in this field has come. Then we'll jump right into mainly looking at insulator oxide systems and how we can engineer spin-orbit interactions in these systems, and finally use those spin-orbit interactions to really drive dynamics to as fast as we can. Okay, so let's begin. So most data on Earth today is actually stored magnetically. So most things you store on Dropbox or in the cloud or box or something like this occur in these or stored in these data centers, such as this IBM data center. And it's mostly magnetic, either through magnetic hard disk drives, or actually magnetic tape is still widely used for long-term storage. And if we take a close look at one of these hard disk drives, you'll see that there are a series of platters. And if you zoom in on these platters or disks, you'll find billions and billions of magnetic grains. And it's really the magnetic state of one or a group of these grains which can represent a 1 or 0 bit of information in binary code. And so this read and write head can essentially read these bits as this disk spins, and this is kind of a staple technology that has really withstood the test of time, right? So this has been one of the most widely used forms of secondary storage for decades, really. And one of the reasons is because this form of memory is extremely inexpensive and it's extremely dense. You can tell by the scale bar here that these bits are on the order of tens of nanometers in size. But there are some obvious drawbacks to this type of technology. Because it's mechanical in nature, it's inherently not very robust. And of course, read and write times are very slow and actually are a function of how fast you can spin this disk. So a good part of the field of spintronics has recently been focusing on designing systems where instead of having something like a hard disk where you have discrete and separate bits that physically move the system, to something more solid state, where instead you have different regions or domains in the material with different magnetic orientations that are separated by finite transition regions or ribbons called domain walls. Now, if you can conceptually drive these domain walls back and forth, you can effectively move these bits in the material in solid state. This has also been conceptualized using 2D variants of domain walls such as skyrmions as well. So this kind of begs the question, okay, if we need to move these domain walls around, so how do we actually move magnetic solitons or drive them into motion? So historically speaking, the only way you can do that is actually by using another magnet or a magnetic field. And actually, this technology has been thought of and almost commercialized. So I think it was in the 70s that Intel and some other companies formed or created and engineered what's called bubble memory. And in these materials, they took relatively thick films. So we're talking either hundreds of nanometers or micron thick films, which they called bubble materials to stabilize two-dimensional spin textures. So these bubbles here. And by designing complicated lithographic tracks, as you can see here, using rotating magnetic fields in the plane, you can actually nucleate and drive these bubbles into motion along these different tracks. So this is called bubble memory. The problem with this type of bubble memory and field-driven motion is that it's extremely power inefficient. So magnetic fields are actually very costly to make. They're difficult to localize. So really this whole chip here all of it sees a relatively similar magnetic field. And of course, if you look at the scale bar in this image, these bits are actually quite large, on the order of microns in size. But what I think is really interesting about this technology is that the same types of materials that they were using for this, what we call now old technology that never commercialized, are the same types of materials that I'll be showing you today. We've just engineered them in ways to make them useful again. So fortunately, there are other ways we can manipulate magnetic textures. We can use things like spin torques or angular momentum transfer. And this typically involves the movement of electrons. And so this can happen, generally speaking, in one of two ways. You can actually use another magnet to create the angular momentum. So you can use something called a spin transfer torque, either in a DC way or a resonant way, such as spin pumping. But the focus today will be on using actually non-magnetic materials to create angular momentum. This is by using the spin Hall effect to create what we call spin orbit torques. And so since this is a focus today, I want to spend just a quick slide on it. So if you take a normal metal, something like aluminum or copper, and you pass a charge current through that metal, you'll find that the spins passing through that metal are kind of randomly distributed and randomly oriented. However, if you choose a system with large spin orbit couplings, such as platinum, tungsten, topological insulators, even some 5D transition metal oxides with large spin orbit coupling, you'll find that electrons of different spins deflect orthogonally in different directions. And this can be more easily seen in this cross-section, where different spins are actually deflecting to different edges of this material. And this is what the spin Hall effect is. So you can essentially, from a charge current, you can create a transverse spin current, and the spin current carries angular momentum. And so essentially, by placing a magnetic material next to one of these large spin orbit coupling materials, you can transfer this angular momentum to the ferromagnet. And this is what we mean by using a non-magnetic material to create angular momentum. And so this is not a new thing. So people have been driving magnetic dynamics in materials using this technique for many years now. Looks like over a decade. And it's even been used to switch the magnetization of materials and even drive domain walls into motion. So this is a great way to elicit soliton motion in films. One thing I've been glossing over is actually that the type of domain wall matters. So you can't just drive any type of domain wall with a spin orbit torque. You need a special kind of domain wall. And domain walls can come in many different flavors. In the material systems we're talking about, they mainly come in two flavors or two types. So in perpendicularly magnetized systems, you can get one of two types of domain walls. The first one is a Néel domain wall, where the rotation of the spins from one domain to another domain occurs parallel to the normal of the domain wall. Conversely, in a block domain wall, the rotation of spins from one domain to the next actually happens perpendicular to the normal domain. And spin orbit torques really only act on Néel type of domain walls, and that just has to do with the symmetry of that kind of torque. So the strength of that torque, or the effective field created by this sort of torque, is proportional to really the angle between that domain wall moment and the domain wall normal. That's what we call this angle psi here. And so block domain walls actually don't feel the torque at all from this from a material like platinum, whereas Néel domain walls will feel the full brunt of the torque. So the strength of this torque is really proportional to the domain wall angle and this term here, which is actually proportional to the current. So you have a current term as well as a domain wall angle term. So what's challenging is that typically magnetostatics dominates what type of domain wall can get in a material. And in thin film materials, magnetostatics says you get block domain walls. So it's actually not trivial to stabilize this special type of domain wall in films. But very fortunately, we can use local interactions, not just long distance interactions, local exchange interactions to stabilize these types of nail domain walls in films. So specifically, we can use the interfacial Drasaligens-Kimura interaction, or DMI, to stabilize nail types of domain walls. So this is nothing new here. What's very convenient is that the same material systems that create these large spin-over torques can actually also induce these interfacial DMI interactions as well. So if you really got nothing from the last slides, if that was really confusing, really what the takeaway message is that in order to move a domain wall using a spin-over torque, you need a few different ingredients. You need a spin-over torque material itself, such as platinum, which can generate this angular momentum. And you need a special type of domain wall. In other words, you need this interfacial DMI interaction. And this really comes from strong spin-over coupling and symmetry breaking, which is inherent at interfaces. So this talk is really on fast domain wall dynamics, or fast dynamics in these systems. And so how do we achieve those? And so really, most of the field for the past decade has really focused on ferromagnet systems. And the problem with ferromagnets is that they're limited by processional dynamics. And we can take a close look at this more carefully. If I just have a toy model here of a magnetic moment M, and I apply a magnetic field in some arbitrary direction, intuitively, you would think that M will want to align towards the magnetic field, but this does not happen in a trivial way. In fact, it's well described by the Landau-Lifshitz-Gilbert equation, or the LOG equation, which describes the magnetization dynamics over time. So what happens to this vector over time under this field? And there's two main terms here. There's a processional term, which actually torques the moment perpendicular to the applied field. This is a processional term. And then there's an alignment term, which actually is the intuitive term, which aligns the magnetic moment towards the field. And so the combination of these two creates what we call processional motion or processional switching, which is really slow and lossy. It's actually often compared to viscosity or viscous-like motion. And it's really this processional term, this first term here, that's responsible for a lot of other undesirable effects that we see in soliton motion. So for example, it's this processional term that is really responsible for fundamental domain wall speed limits that we see in materials. This plateau that you see is a direct cause of this processional term, or a consequence of this processional term. It's also responsible for Walker breakdown, or the reduction in domain wall mobility at high magnetic fields. And this processional term is actually also responsible for the skyrmion Hall angle, which is the undesirable effect where the skyrmion moves in an angle that is not along the direction of the current flow. Very fortunately, what our group, and as well as a few other groups, have discovered in the recent years is that we can actually use different classes of materials to overcome these limitations. So rather than using ferromagnets, we can use multi-sub-lattice magnetic systems. So these are things like anti-ferromagnets or compensated ferrimagnets to overcome these. And very simply put, in the case where you have very large exchange coupling in these systems, you can actually modify this LOG equation. And what you find is that in compensated systems, you actually eliminate this first term, which is a processional term. So when the system has no angular momentum, you actually only get direct alignment of the spins along the direction of the force. So it's almost like Newtonian motion rather than processional motion. And so our group, as well as a few other groups, have shown this is possible in metallic systems, rare earth transition metal systems, such as gadolinium cobalt, terbium cobalt, and some of those alloys. And in particular, we experimentally showed how we can get rid of at least one of these negative effects that's seen in ferromagnets. In fact, here I've plotted velocity as a function of current density. You can see when the system is perfectly compensated, you only get linear dynamics, and you can avoid this fundamental velocity plateau seen in ferromagnets. In fact, you can engineer the angular momentum in these systems either with composition or temperature. And if you do that such that you introduce angular momentum back into the system, you see that the material behaves more like a ferromagnet. So this is great. We can use these types of new systems to really overcome some of these fundamental limitations that ferromagnets give us. And here's just a couple other examples of other manuscripts, published works, which show how you can use ferrimagnets, compensated systems to overcome some of these other processional dynamic issues, such as the skyrmion Hall angle. Okay, so hopefully I provided you a bit of background on compensated systems and domain wall dynamics and compensated systems. What I'd like to do now is really jump into different classes of materials and why they're actually more advantageous over metal systems. So what I've shown you so far, and really what the field has focused on for the past few decades, is really metallic systems. So these are tri-layer systems like ones I showed you earlier, multi-layer systems, which can host skyrmions, other types of textures. And even the systems that I showed you have some of these linear fast dynamics actually occur in metallic systems as well, as shown by our group as well as some other groups. And really, metallic systems are great, simple systems to study these phenomena, but they have some major drawbacks. So for example, metallic systems by definition are conducting. So not all the current that you pass through these types of devices goes through the torque generating layer. So you actually have some loss. The other thing that we have to consider is really the mobility of the domain wall as it travels in the materials. So the velocity of a domain wall is really proportional to this term out front here. And so if you look closely at the domain wall mobility, you'll see that there are a few things that affect domain wall mobility, at least in the simple sense shown here. There is, of course, the domain wall width, there's the gyromagnetic ratio, and this alpha term on the bottom is actually the damping. So this gyromagnetic ratio is relatively constant. Domain wall width in these types of materials, you can really only vary by maybe an order of magnitude at most. But this damping term at the bottom is really what's hindering the domain wall speeds or the domain wall mobilities in metallic systems. This can be quite high in metallic systems. But very fortunately, just through materials engineering and material selection, we can actually vary this parameter by several orders of magnitude, thereby increasing the domain wall mobility by several orders of magnitude as well. This is a very tunable materials parameter that we can use towards our advantage. And really, insulating systems are well known for having low damping. And in particular, rare earth iron garnets are systems that are really famous for their low damping, and they're often taken advantage of for their low damping. So rare earth iron garnets take the chemical form, a 3,5,12 chemical form, and they actually have an extremely complicated unit cell. There's well over 100 atoms per unit cell here in various different sites. But fortunately for us, magnetically speaking, they're relatively more straightforward. There's actually 3 magnetic sublattices.
It looks like
this.
Hey, Lucas, I think we lost you for about 30 seconds. Can you?
Oh, sure. Yeah, I can back up a slide. How about that?
Thank you.
Yeah, no worries. I'll just start here. So really the advantage we can take in increasing domain wall speeds is really by engineering this mobility parameter. And the easiest way to do that is by actually tuning the Gilbert damping parameter, which is alpha, which is something we can vary by orders of magnitude. And so insulating systems are actually very well known for having low damping. And in particular, rare earth iron garnets are a classic example of this. They're famous for their low damping. And they take the chemical form, a 3,5,12 chemical form. And so they actually have a really complicated, complex unit cell, which has over 100 atoms per unit cell in various different sites. But fortunately, magnetically speaking, they're actually relatively straightforward. There's just 3 magnetic sublattices in these materials. There's 2 iron magnetic sublattices and 1 rare earth sublattice. And the interactions between these different sublattices are as follows. So the tetrahedral iron and the rare earth dodecahedral site are coupled through superexchange. So they're anti-parallel aligned. And the 2 iron sites are also coupled through superexchange, and they're anti-parallel aligned. Now, the interaction between the octahedral site and the rare earth is typically weak, so we kind of neglect this term. So we essentially have 3 magnetic sublattices here that are anti-parallel aligned. And the beauty of these material systems is just by selecting which rare earth, or frankly, lack of rare earth we put in this dodecahedral site, we can dramatically change materials properties. So here's an example of a saturation magnetization as a function of temperature for different rare earth materials. And just by choosing different rare earths, we can drastically change what the magnetic compensation of this temperature is and the magnetization as a function of temperature while still retaining high Curie temperatures. So these are extremely tunable systems with very desirable properties. And what I'll show you is that not only can we tune the magnetization, we can also tune things like the anisotropy, the damping, which is very important for domain wall motion and domain wall mobility, as well as these compensation temperatures. And it's really this low damping and the tunable damping systems, which is what they are like really famous for. So they've been studied for decades, looking at things like long spin wave propagation lengths as high as centimeters in length. You can even more recently use these material systems with spin orbit torque metal overlayers to actually use transport-based sensing of an insulating system. So you can do a lot of very cool things with these very historic and well-known systems. However, so these are actually the same material systems that some of the original forms of bubble memory were based off of, but it's only really recently that we've been able to grow these systems, such as thulium iron garnet, at very, very thin thicknesses using atomic scale synthesis, such as pulse laser deposition and really advanced forms of sputtering. And by thin, I mean thicknesses that are about 10 nanometers in thickness or even less. And by growing such thin materials, we can actually take advantage of interface interactions that occur in these material systems. So for example, we can use strain from substrates to induce perpendicular magnetization through magnetostriction in these materials. We can even grow heavy metal overlayers and induce very large spin-over torques in these systems, large enough where we can actually switch the magnetization and generate torques that are on the order very similar in magnitude to traditional metallic systems as well. However, the missing ingredient for domain wall motion in these systems has really been the stabilization of these special types of Néel domain walls. So really, the lack of DMI in these material systems has been hindering the current-driven propagation of domain walls in these materials. And so this is kind of what we set out to look for in these material systems. And so what we did was design domain wall racetracks, as you see here, where we can actually nucleate a domain wall and drive it into motion, and actually probe the position of this domain wall using the magneto-optic Kerr effect. So after we nucleate a domain wall, we can actually drive it into motion, here just using a simple out-of-plane magnetic field to drive this domain wall into motion. And we use a time of flight technique to actually track how long it takes for this domain wall to travel past this laser spot. So here's a plot of the arrival time, or the time of flight, as a function of distance that this laser is away from this domain wall for various different magnetic fields. And you can actually plot this out, and if you take the slope of this curve, this is the velocity of the domain wall. So here I've plotted the velocity of the domain wall just as a function of magnetic field, or actually inverse magnetic field, and that's why it goes down. And so this is a useful way to really probe domain wall motion in these systems using a very straightforward time of flight technique. Now, we can also add a current to the system as well. So these systems have a platinum overlayer. We can also drive a current through that platinum overlayer at the same time that we're applying a magnetic field. Now, if you recall, these spin orbit torques don't act on block domain walls at all. So really, if we pass a current and the domain wall is a block domain wall, really our velocity curves that I showed you on this previous slide shouldn't change at all. Really, the current should have very minimal impact on the domain wall velocity. However, if this domain wall is of Néel type, then this torque will actually act on that domain wall and either help push it forward along with the field, or actually counteract the field and hinder its motion. And so what we did was actually we calculated or measured the depending field of this domain wall. So we drove this domain wall with both a field and a current, and we tracked the domain wall depending field as a function of current. And what you can see here is the depending field actually is a strong function of the current. So depending on the polarity of the current, we can actually either decrease or increase the depending field of the domain wall. In other words, we can actually help push it forward or actually hinder its motion just by changing the current. And what this means is that there's actually a sizable torque that acts on the domain wall. And we can do this for both up, down, and down up domain walls. We can quantify the size of this torque just by the slope of this curve. So this tells us the amount of effective field per unit current density that we are applying to this domain wall. And if you do that calculation, you'll find that this effective field is actually quite large. It's very similar to what's seen in metallic-based systems. But more importantly, what this implies is that we actually have Néel type of domain walls in the system. So, and the symmetry of these curves actually tells us that these are chiral domain walls. So we've actually shown that we actually can stabilize chiral Néel domain walls with these ultra-thin garnet films. In fact, we can quantify how large that DMI is. I can prove to you further that there is DMI. So this is a similar curve I showed you before. This is the depinning field as a function of current. And you can see that we can either hinder the domain wall's motion or decrease the depinning field. Now, if I apply a magnetic field to this system, a small magnetic field, so not large enough to really cant the magnetization in the domains, but large enough where it can actually rotate the domain wall itself towards a block configuration, you can actually see that if we apply a field that is equal to the strength required to transform this domain wall from Néel to block, we can actually turn off this torque, so to speak. So you can see on the plot on the right here that the current has no effect now on the depinning field of this domain wall, meaning that it's completely blocked. And this field that's required to do this is actually the DMI field. So it's a way to quantify the DMI in this material. In fact, if we apply a field that's much larger, that's actually large enough to completely rotate this domain wall from a left-handed domain wall to a right-handed domain wall, you'll see that there's an inversion, complete inversion of the sign of this torque. So we can really quantify not only the strength of the torque as a function of the domain wall orientation, really, we can also quantify the DMI in these systems. A more explicit way to show this is actually if I plot the slope of this curve here as a function of in-plane field. So if you plot the slope of this curve as a function of in-plane field, you'll see the plot on the left. And so, for example, at zero field, you see some non-zero torque. If I apply an in-plane field to rotate the domain wall from Néel to block, you'll see that that torque goes to zero. In fact, I can invert the sign of the torque just by applying a large enough field to completely flip the domain wall. And we can do this for both down-up and up-down domain walls. You actually get something that's very neat. It looks like a hysteresis loop. And so really the zero crossing, or the coercivity, so to speak, of this loop is the DMI effective field in this system. And we can do this actually for a thickness series of TMIG. So here you see these same different curves, except for a thickness series of thulium iron garnet. And what you find is if you plot the DMI as a function of thickness, you'll see that it scales inversely with the thickness. So the thinner the film, the larger the DMI. This tells us that the origin of DMI in this film is actually interfacial. So we do see an interfacial DMI in this system, but the question still remains, which interface is it coming from? So the intuitive answer would be, it must be coming from the same interface that it comes from in metallic systems, that is the heavy metal garnet interface. But in fact, and I'll mention that we're not the only people to do this. There are several other groups that have shown this, and I want to give credit to them as well, that show a similar dependence on thickness and also see these chiral types of domain walls in these films. But what's interesting about this material system is that if you compare it to a traditional metallic system, the domain wall rotation is identical to that you would see in a metallic system, except in our systems, the platinum's actually on the top. And so this is very peculiar. You wouldn't expect to see this if the DMI was indeed coming from this platinum garnet interface. In fact, this is probably a bit easier to see if I flip the garnet system over. You can see that it has identical domain wall rotation, but the platinum is actually on the opposite side. So what this tells us is the DMI is likely predominantly not coming from the platinum layer. And I'll prove this to you further in the next couple of slides. And so to prove really the origin of where this DMI is coming from in these insulating systems, we actually grew a different type of magnetic insulating garnet. This time we have a different rare earths, terbium instead of thulium. And what we find is when we measure the DMI in this system, DMI is actually 4 times smaller than it is thulium iron garnet, everything else being the same. So just by changing the rare earth, we can significantly change the DMI in this system, meaning that the rare earth takes large responsibility in the strength of the DMI. Moreover, if we put a small copper spacer layer between the platinum and the garnet material, what the spin transparent layer does is still allow us to torque the domain wall, but it really kills or gets rid of any interfacial effects that would be coming from the platinum layer. And when we do the same measurement, we actually find is that the DMI actually increases when we put this copper spacer layer between the platinum and the thulium iron garnet. So what this tells us two things. One is that the platinum actually has a very little role in the DMI of this material system, and predominantly the interfacial DMI is actually coming from the substrate garnet interface. We can also grow a film which actually lacks any rare earth. So if we take a different material system, this is bismuth substituted YIG, so there's no magnetic rare earth system, what we find is that the DMI becomes negligible, it actually goes away. So the zero crossing here is actually at zero field. So these domain walls are inherently blocked. So this tells us that, once again, the platinum likely plays little role in the DMI in these systems, and that really it's the rare earth in these materials that is the main function, or the main predominantly contributing factor to the DMI. So a lot of the spin-over coupling actually comes from the rare earth element and not the platinum. Moreover, we can engineer the strength of the DMI not only through composition, but also through strain. So by choice of substrate, we can strain the garnet in different ways and actually induce different strengths of DMI. So we can change the DMI by up to a factor of 2 just by using strain. So very similar to how the magnetic anisotropy is sensitive to strain, also the DMI is as well. And to further prove that the DMI is a function of the rare earth in these material systems, what we did was we went to the synchrotron and did some XMCD studies at the thulium edge of these materials. And through XAS and XMCD, what you can actually calculate is both the spin and orbital angular momentum of the thulium as a function of temperature. And essentially, you can calculate a parameter that goes as spin-orbital coupling. So you can basically calculate what the spin-orbital coupling is in these systems as a function of temperature. And this inset here is just a zoom in of what it is from 200 to 400 degrees. And what you find when you measure the DMI as a function of temperature is that this closely follows what you see in the spin-orbital coupling of the rare earth material. So this is further evidence that the DMI actually follows the spin-orbital coupling of the rare earth material. But I think from a physics perspective, why this is interesting is you can also see that the DMI or the spin-orbital coupling increases by an order of magnitude at very, very low temperatures. So this might suggest that the DMI in these materials might actually be very, very high at low temperatures as well, meaning that there could be spontaneous formation of chiral textures and these other things at very, very low temperatures, which still hasn't been measured. Okay, so this is great. So what we have now is a material system which has perpendicular magnetization, has a large spin-orbital coupling, which can be tuned from the rare earth element. We can induce DMI in these materials and create chiral domain walls that, and really what this tells us is that we have all the ingredients that we need for ultra-fast dynamics in these materials, including low damping from these garnet systems. And so what we can do is drive domain walls in these systems which have DMI. And so when we do that, we created racetracks of these material systems where we can nucleate and drive domain walls. And here I've plotted the velocity as a function of current density in these material systems. And you can see that for very thick thicknesses, when the DMI is actually quite, the torque is low and the DMI is actually quite low, the domain walls don't move particularly fast. But as we decrease the thickness of the thulium iron garnet, you can start to see non-zero velocities. In fact, what you see is there's a linear regime and a plateau regime. And this looks like actually classic, what a classic ferromagnetic domain wall would look like. So there's a linear regime, which is proportional to the current, and a plateau regime, which is actually proportional to the stiffness of the domain wall. Or in fact, in this case, how large the DMI is in these systems. And the reason that this plateau regime occurs is the following. So when you torque a domain wall in a ferromagnet, what happens is not only does that current drive the domain wall into motion, it actually torques it towards a block configuration as it does so. So the torque, the effective field on these material systems is proportional to both the current and the character of the domain wall, or how nail that domain wall is. And so if you're not only So as you increase the current, if you're torquing this domain wall towards a block configuration, these two things effectively balance and you get a plateau in velocity. And of course, you can adapt this model as well to ferrimagnets, which is what we did here. And you get a similar result when you're not right at perfect angular momentum compensation. So what this really means is that the thinner we go, the higher the DMI is, the higher the torque is, so we should see higher plateau velocities, and that's exactly what we find. We find that the plateau velocity is proportional to the strength of the DMI. And to prove that this is a DMI-limited plateau, I can actually apply an in-plane field in addition to the DMI to help stiffen that nail character of the domain wall. You can see that we can overcome this plateau that we saw before. And really, what I've been glossing over is really the axis on the left here. So the domain wall velocities that we are able to see in these systems are several thousands of meters per second. So seeing these velocities, we really ask ourselves, what actually limits the domain wall velocity in these magnetic systems? Which takes me to the last part of the talk, which really goes into the fundamental limits of how fast domain walls can move in these material systems. And so what I'll show you in this last part of the talk is really how domain walls not only obey Galilean relativity, but also Einsteinian special relativity as well. And so, theorists have predicted for several decades that a fundamental domain wall velocity exists in these types of material systems, and they prove this that the governing equations for this are the Sine-Gordon equations, which are equations that look very similar to those that govern electromagnetic fields. In other words, that the max velocity expected in these systems is not the speed of light, but in fact, it's the speed of a spin wave. So another way to conceptualize this is that traveling domain walls are actually solitons, or solitary waves, which are superpositions of spin waves. And so the max velocity that a domain wall can travel is really the spin wave group velocity. And really with the resurgence of compensated systems in this field, like antiferromagnets, there's been a lot of recent studies that show that antiferromagnets and other compensated systems, these are done numerically and analytically, can host these ultra-fast velocities, which are usually inaccessible in ferromagnetic materials. So to really access this type of physics, we actually turn to this material system, bismuth-Ytterbium. So the lack of rare earth in this garnet actually means the damping is even higher. It's about an order of magnitude higher than it is in the rare earth iron garnets, which means that domain wall mobility is even faster. But if you recall, the domain walls in the system are actually block domain walls. So they're inherently immobile, meaning that they won't move with spin over torque on their own. So they're this type of domain wall, this block domain wall. So what we did in this experiment is actually once again go to our in-plane field. So we apply an in-plane field to cant this domain wall from a block configuration to a nail configuration. And the amount of field it takes to do this is actually not very high. The domain wall anisotropy is very, very low. It's at least one order of magnitude lower than the anisotropy of the bulk of the film. And so what we've done is created domain wall racetracks where we can nucleate domain walls in this system. This is imaged by Kerr microscopy. And here we can apply a magnetic field to force a nail domain wall configuration. And by doing so, we can drive domain walls with currents in these material systems at very fast velocities. This is more explicitly shown on this plot, where I've plotted that velocity saturation as a function of in-plane field. And of course, at zero in-plane field, when the domain wall is block, the domain wall doesn't move at all with the current. And as we increase the in-plane field or the stiffness of the domain wall, increase the nail character of the domain wall, this plateau increases. And here's a more familiar plot of that. So here I've plotted the velocity as a function of current, and we can see that it follows a typical 1D model with a linear regime, a plateau regime. And as I increase the in-plane field, in other words, increase the stiffness of the domain wall, this plateau regime increases as well. What's very peculiar is that if I keep increasing the in-plane field, in other words, you keep increasing the stiffness of the domain wall, these curves begin to stack up on top of one another, meaning that the domain wall is no longer limited by the stiffness of the domain wall. You can see this plateau occur as well in this plot. So what this basically is telling us is that no matter how hard we drive the domain wall with the current, no matter how stiff that domain wall is, it won't move any faster. And there's really no current model that can explain the phenomenon that's happening here. But what I'll show you is that it actually can be easily explained using Lorentz contraction and relativistic physics. And so what we've done is actually calculated the exchange mode spin wave dispersion for our material using only experimentally derived parameters. So there's no textbook values here. These are all measured in our material system. If I plot that dispersion relationship, it looks like this. And so if I take the derivative of this dispersion relationship, I get the group velocity of the magnon, which peaks, or excuse me, which saturates at around 5,000 meters per second. If you remember on the previous slide, the velocities that we're seeing in the system are on that order, very close to 5,000 meters per second. And so what this tells us is that we actually have to use relativistic physics to account for what we're seeing in these material systems. We can also analytically and numerically, using atomistic simulations, compute what the expected Lorentz contraction of the domain wall is as a function of domain wall speed. And from our dynamics data, we can actually infer what this domain wall width is, as well as a function of velocity. And this, what we find is that using our experimental data, the domain wall width closely matches what you would expect from a Lorentz contraction. So we can take this Lorentz contraction model and this Lorentz contracted domain wall width, excuse me, and adapt our ferrimagnetic one-dimensional model to account for these Lorentz contractions. And when we do so analytically and both using atomistic numerical models, we see the following data. We see data that very closely, both qualitatively and quantitatively, matches what we see in the experiment. So what we've shown here is that what we're seeing in our experiment is actually what we're reaching is the fundamental domain wall velocity limit in this system. So what this really does is kind of opens a new door or platform to really study relativistic physics using tabletop experiments in your lab. And also for practical reasons, kind of uncovers the fundamental limits of how fast these things can move. How fast can these types of domain wall devices actually perform? And tells us the underlying materials parameters that we can use to kind of maximize these speeds. So just really quick at the end here, I know I'm basically out of time. What I'd like to pitch is that there's other ways we can manipulate magnetic solitons in these systems, and we can actually use ultra-fast light to do this as well. So in these same compensated systems, these same ferromagnetic alloys, not only can we drive dynamics with currents, but also with light. So these are the same material systems where you can do what's called all-optical toggle switching. You can switch materials using ultra-fast femtosecond light. But instead, what we're doing here in this experiment I'm about to show you is that we're actually taking advantage of what is often criticized about these rare earth transitional ferrimagnets. So we're taking advantage of their temperature sensitivity. In fact, very close to the compensation temperature, the domain wall energy is very sensitive because the magnetization is also very sensitive as well. So what we do is actually use very low light, lower energy than it takes to switch the material using light to actually drive domain wall dynamics using heat. And what we find is that we can only do this in materials that have DMI and when they're close to compensation. So we can actually drive domain walls back and forth on these materials just using light alone. So no magnetic fields, no currents, no pattern devices at all. And we find that it's a strong function of the DMI in these materials as well. And we can even do this with topological skyrmion bubbles as well. We can drive domain walls and bubbles back and forth in these materials as well, all optically. Okay, with that, I'll wrap up. I think I've eaten too much time anyway. So I hope I've shown you that we can really use magnetic excitations like domain walls, bubbles, and solitons as really a platform to study new physics and new technological impact simply by using atomically precise growth and a variety of in situ imaging techniques. So with that, I'll thank the variety of staff, other scientists, students, PIs, and labs across the world who have helped, were instrumental really in putting this work together. And I'll finally end here. And thank you for your attention, and I'm happy to answer any questions.
Thank you very much for the very interesting talk. This talk is open for questions. So if you're in Zoom, please use the raise hand function. And if you cannot find that, you can always send me a private message and I read it for you. And if you're watching this online on Twitch, please also ask a question using the chat box. The first question will be asked by Dr. Patton. Please go ahead. Dr. Patton, you have to unmute yourself.
I've been calling my colleagues here at CSU during this talk to say they should get their butts on the screen and watch it, because this was an incredible talk, Lucas.
Appreciate it.
You're carrying on a great tradition. And I could ask you a million questions, but I'll just ask two. I did make a comment in the chat. I don't mean to be an old curmudgeon, but my first ever talk in 1964 was on forward and reverse Néel walls in permalloy.
Okay.
And nobody knows about that paper. It was horribly written because I didn't know how to write back then. But would you send me your email address, by the way?
Yeah, sure. I'll put it on. I'll put up the home screen.
Jeff should know what it is, but okay. My two questions are, I've always understood that domain walls are like solitons because at least the microwave solitons I've studied for a decade or so have the same functional form, the hyperbolic sign, I think it is. But what I remember from our work and working with theoreticians at University of Colorado is the basic equation is what we call the nonlinear Schrodinger equation. And it's a fun equation. Mark Ablowitz at University of Colorado has been the pioneer in what do you call it, reverse Fourier transforms or something. I don't remember the details.
Sure.
But that's a real nonlinear problem, the nonlinear Schrodinger equation. The way I understand domain wall motion in magnetic films, and of course you've taken this further than I ever did, but my thinking is that you have a domain wall, and when you apply a field, it distorts a little bit. And when it distorts, it produces a driving field that the magnetization processes around, and that's how the wall moves. Yep. It's a concept from the 60s. But it's essentially a linear problem because the distortion of the wall is very small. And of course, when that distortion gets to 45 degrees, that's when you get your saturation of the thing. So yeah, that's my old understanding. Now you've advanced this picture a lot more. So why is that a nonlinear problem? And until you get close to the saturation limit. That's my first question.
Okay, I'll see if I can understand your question. Maybe it goes back to some of the earlier slides that I showed here. So you can describe, I think, what you're saying, field-driven motion using this expression, the LOG equation. I think that's what you're talking about, this processional-driven motion. Right. When you look at spin-orbit torque-driven motion or current-driven motion, you actually get a bunch of other terms here as well. So it's not as straightforward as this. I'm oversimplifying it in this case. So there are a variety of other terms here, and those are actually important terms that torque the domain wall itself as well. So okay. I very much gloss over it, but there are other terms as well that factor into play here. And I'm simplifying.
Okay, well, that's above my job description, so but
okay.
I know what to think about, so that's great. My second question is, your last, I mean, this talk went really fast.
Yeah, I apologize.
But the velocity, you talked about relativistic effects. Yes. And again, you were zooming too fast for me, but this mass of the domain wall is velocity dependent. And that's a relativistic effect because the mass of particles, relativistic particles, the mass depends on the velocity. Am I thinking wrong about that, or is it?
Yeah, you cut off for the first part of your question, but I think I understand what you're getting at. So basically, domain walls in magnetic films can obey Einstein relativity in that they will see time dilation if they move fast enough. They will see Lorentz contraction if they move fast enough, and they will also see velocity saturation as well. So
Okay,
the faster the domain wall moves, the more its length will contract, and that has it's
Right.
very equivalent to Einsteinian relativity, where you'll see effects with mass, you'll see effects with time dilation, and all these other things as well.
Okay. Anyway, amazing talk.
Thank you.
I'm too old to be thinking this hard.
Well, I'll tell you, we still use permalloy a lot today, so.
Thank you for the question. I'm going to read a question by Professor Jacob Gales. He asked, this is an amazing talk. Sorry, very nice talk. Can I ask why the dynamic of the ferrimagnetic domain walls does not approach the antiferromagnetic domain wall limit?
I'm not sure I quite understand the question. I don't know if Jacob is still on.
Jacob, are you here? Maybe you can help clarify the question.
Yeah, sorry. It seems that, and so in the case for antiferromagnetic domain walls, they use, I mean, you have the dynamics of both spins here, yeah? And in your case, you lose the dynamic of both spin lattices.
Yeah, so what this model is a simplified version of that. So in this case, what we assume is that the two sublattices are so have such high, essentially infinite exchange between the two sublattices. So we can really just represent both of these sublattices by one, which is a net sum of the magnetization and the angular momentum of both of them together. So this is not a two sublattice model. It's actually the limit of the two sublattice model in the high exchange limit. I hope that answers your question.
I mean, usually, well, in antiferromagnetic cases, usually the exchange is quite large, right? And so even with the large exchange, the speed is increased because the exchange is large, right?
Yeah.
You cannot separate the two sublattices.
Yeah. So basically, I mean, in these material systems, when they're perfectly compensated, so when the angular momentum is zero, they behave exactly like that as an antiferromagnet would, dynamically speaking. So there is no difference in that sense. So what we have here in this, at least in the case of this relativistic domain wall motion, the reason it doesn't look quite like an antiferromagnet is because it's not perfectly compensated. So you still have to account for some angular momentum in the system. I'm not sure that answers your question, but hopefully.
Yes, thank you very much.
Okay.
Thank you. Do we have other questions?
So I have a question, but I cannot raise.
Right. Go ahead, please. Yeah.
Okay, so like you need to have magnetic field to drive the main wall in antiferromagnet. So do you think field-like torque can be useful to replace this external magnetic field, perhaps maybe using some lower symmetry interface?
Yeah, so the only, at least for this last part of the talk, the only reason that we use the field is to stabilize the nail domain wall. So if there's another way to do that without having to use a magnetic field, then that could work. We have to keep in mind is some of these other things like if your damping is too high, I think DMI breaks Lorentz invariance, right? So you won't see the relativistic effects if you start bringing in some of these other materials properties into play. So this bismuth-Yig is a perfect system in that it's extremely low damping, so there's no other dissipation mechanisms. There's no DMI, so you don't break Lorentz invariance in that sense, but we can still use a magnetic field to kind of manipulate the domain wall how we want. So the short answer to your question is, yeah, there are other ways that you can probably get this sort of dynamics. You just have to be careful with how you introduce these new properties.
Okay. Yep. Thank you.
Great. Do you have other questions?
And if you need if you want a copy of the slides or have any other questions, my email is right here. I'll make it bigger.
Yeah. Let me ask you one question as for the relativistic effect of the domain wall motion. Can you just let me know if my understanding is correct? So
Okay.
basically, the domain wall just cannot exceed the speed of the spin wave. So in the sense that in the magnetic medium, the fundamental speed limit is spin wave. That's as fast as the magnetic information can transfer through this medium. So therefore, as the domain will start to approaching that speed limit, this is more analogous to the Einstein's relativistic effect, as no speed can be faster than any information transfer.
Yeah, that's correct.
Okay, and I was also thinking another analogy, because the spin wave is the speed for the spin information to transfer through the magnetic material. It's like the media. It's like what's that? A sonic boom. So is it possible? So it can never exceed the speed of the medium, or it is actually possible, and it can even create a boom of the spin waves?
Yeah, so you can. So it's predicted that you can see things like Cherenkov radiation or Cherenkov-like radiation from moving domain walls, and in an antiferromagnetic system, you'd expect that to be like terahertz spin wave emitting from the domain wall. So that's been predicted. You won't see this plateau if you break Lorentz invariance either, right? So you can. I mean, the plateau exists here because we've selected and engineered a material system to have the plateau, but there are other predictions of other papers and simulations where you can actually go above this plateau just because you're not breaking Lorentz invariance. So the short answer to your question is, in this material system, this is as fast as you can move domain wall. In principle, you can go faster than this in other material systems, and you can see effects like Cherenkov-like radiation, most likely, at least it's predicted. We see, when we drive the domain wall at this velocity, there are some odd things that we see that we can't explain yet that might look like Cherenkov radiation, but we're not sure yet, which is why I haven't really talked about it at all here. So definitely you're on the right track with the interesting things you can do here. And I'll point out that this speed limit of close to 5,000 meters per second is very materials dependent. And it's a function of the exchange as well. So if you, light switch. So if you choose a material system with different parameters, you can go to even faster velocities. So something like gadolinium cobalt, actually if you take textbook gadolinium cobalt, those materials parameters, and plug it in, and try to calculate the max spin wave velocity, it's something like 25,000 meters per second. So it's much higher. So different materials have different limits. And so this particular case of bismuth-Dieg, this limit actually happens to be relatively low and accessible for us.
I see. Thank you very much for the explanation. Looks like Li Jun turned on. Do you have a question, or does anybody have a question?
I have a question. I forgot how to raise hand. Sorry. So I have two questions. First one is, you show that platinum oxide interface is not important for DMI, but for metallic system like a platinum cobalt system, this interface is very important for DMI. So what's the difference between metallic system?
I'll say maybe I'll restate what you're saying. It's not that it's not important at all. It's just significantly less important. So there's some other works, not just work that I'm showing here, but there are some other works which show that the platinum contributes a little bit to the DMI.
Yeah. Okay.
But what we find is that the other interface contributes even more. And in fact, it looks like they're opposite inside, right? So you have a big effect from the bottom and a small effect from the top. And it's really the effect from the bottom interface, the substrate interface, the oxide-oxide interface. The symmetry breaking comes from the interface, but the spin-orbit coupling comes from the rare earth, is what we find. So that's the difference. So in the metallic systems, both the spin-orbit coupling comes from the platinum, and the interface break and the symmetry breaking comes from that interface as well. What we find is in the oxide systems, the symmetry breaking comes from the interface, but the spin-orbit coupling doesn't come from the torque material. It actually comes from the magnetic material itself. That's the main difference that we see.
Yeah, so you say it's an interfacial DMI. So does that mean it's from the bottom interface with the substrate?
Yeah, that's exactly what we do. Yep.
Okay.
So perhaps choice of substrate. If you picked a different garnet substrate, you can dope these substrates. You can buy commercially doped substrates. That will very likely change the DMI as well, depending on how you dope it or stream.
Okay. Yeah. I think since spin of the carbon is from the oxide, then it should be the same for the two interfaces, right? So what's the mechanism so that the DMI magnitude is so different for the two interfaces?
Yeah, that's a good. Yeah, so this top interface is inherently different from the bottom interface. So it's not the exact same interface here, right? So this is a metal oxide interface, this is an oxide interface. The mechanism by which it happens is still unknown. So there hasn't been any theory or modeling work done yet on the intrinsic.
Could that be like orbital hybridization stuff?
Yeah, it could be from a lot of different things. It could be from hybridization at the interface. It could be from, there's no charge flowing here, so it's not charge transfer. But there's a lot of things that could be coming from, and it just hasn't been studied yet. It's actually a big open question.
Okay, thank you. My second question is, I actually showed the papers they show in metallic ferromagnetic system is a very high domain velocity.
Yeah.
Velocity. Yeah. So I think damping in that system should be high, right? So what's the reason this domain velocity speed is so high?
Yeah, so the speeds here are high, so they're on the order of 1,000 or 2,000 meters per second. And that's because, and that only really occurs right at the compensation temperature. If you're far away from the compensation temperature, it drops off somewhat dramatically, right? So these systems are perfectly compensated where they have no angular momentum at all, right? The garnet systems are not quite perfectly compensated. They still have some angular momentum. So they're going to behave not exactly like an anti-ferromagnet would. Essentially, yeah.
Yeah, so you mean at the compensation point, the moment is very small, so the torque field is very large? Or?
Yeah, it's not that the moment is small. In fact, if you look at this, there's two lines, the very faint lines that you see here, and I didn't label them, but this line here, this peach, orange, brownish line, that's the magnetic compensation. And this green line is the angular momentum compensation. Yeah. So actually, the magnetization has no effect on the dynamics. It's not in the equation at all. It all has to do with the angular momentum. So the dynamics are only fast when the angular momentum.
Yeah. I'm thinking, what's the mechanism? Like you give a equation.
Yep.
And it shows that the speed is inverse to the damping, and the spin-torque field. Yeah, it's proportional spin-torque field times gamma times domain wall weight.
Mm-hmm.
So I'm thinking that which parameter makes the speed so high at the angular momentum compensation point?
It's really none of those. It's the fact that there is no. Here, let me show you another plot.
Okay.
Maybe I have it in here. I think I do. So it's really the fact that maybe it's on this slide. So that expression I showed you was for the domain. So there's like a V equals some mobility times some field. Sorry, that's
right.
And this mobility is a function of damping and some other things.
Right.
Yeah. So that domain wall mobility is essentially the slope here, right? Now, in a compensated system, it's always linear. In a non-compensated system, so a ferromagnet, you have a linear regime, but you also have a plateau regime. And this plateau regime has nothing to do with this mobility. It actually has to do with the stiffness of the domain wall.
I see.
So it doesn't have to do with the damping, actually.
I see.
And so in a ferromagnet, even if you were to have extremely low damping and it would shoot up really quickly, it would always plateau here, just because this plateau is independent of the mobility.
I see.
So the reason we get fast dynamics in these compensated ferrimagnets is not because of the mobility. The mobility is actually not that great. It's actually pretty crummy. It's just because it's always linear. You never hit the plateau.
I see. I see.
Yeah.
Okay. Thank you very much.
Yeah.
So can you also probe relativistic physics with compensated ferrimagnet, like in the last part of the talk, or there are some problems here?
You should be able to. There's nothing, I can't think of anything that is fundamentally wrong with that.
Can you then also use some magnon group velocity to estimate the maximum domain wall speed?
Yeah, so you can do that. So I know, so there are certain garnets that actually, if you pick that rare earth right, they compensate close to room temperature, I think. So like, I think gadolinium iron garnet has a very close to room temperature compensated system, compensation temperature. I believe the damping is much higher in that system because it has a rare earth. But in principle, if you had an anti-ferromagnet with low damping, you're able to access or have basically a material system that can support relativistic or these high velocities, then you should in principle be able to see it as long as you don't break the lens invariance.